Hello, my name is Thomas Harder. I am faculty and cooperative extension specialist with the University of California at Davis. With this video, I want to talk about groundwater and maybe explain a little bit about what may happen to your groundwater during this drought, or any other year for that matter. California has a fundamental problem with water. We have both a temporal, a time disconnect, and a space disconnect between where we have water available and that is where it rains, and where we actually use the water. If you look at this map, you can see that most of the rain falls in Northern California. We have places with more than 50 inches of rain in a normal year. But most of us use water in the central part of California and in the southern part of California, where we have 15 inches of rainfall, and down in Southern California, less than 5 inches of rainfall. What we have done to both bridge the temporal or time disconnect and the spatial disconnect is we have built storage reservoirs that help us save the rain that falls in the winter for use in the summer. And we have built a large infrastructure of canals and canal networks funded by the federal government, funded by the state, and funded by local agencies to bring water from the north, where we have lots of rainfall, to the south, where we have very little rainfall. Groundwater is a very big part of our water supply. Groundwater is about 40% of the industrial, urban, and agricultural water supply in an average year. That's about 16 million acre feet. What I want to do in the next few minutes is give you an overview of what is groundwater, give you a little bit of an understanding of how groundwater works, tell you how and where groundwater is in California, and very briefly talk about how we manage groundwater and how we make decisions about groundwater in California. So let's start with the question, what is groundwater? Groundwater is very mysterious to many people. We can't see it. Some people think of it as water in arteries flowing around. Some people think of giant reservoirs that are somehow built underground in big caverns. But what groundwater really is like that water that you would pour in a flower pot that just disappears in your soil. And what it does, it fills the pore space between the particles, the soil particles that are in your flower pot. And our groundwater in California is much the same way. It fills the pore space between sand and gravel pieces, even between small, tiny clay particles and silt particles, or it can fill the fissures and cracks in the rocks that make up our big mountain ranges in California. Most of the water in California will be where the pore space is very large. That is between sand particles, between gravel particles, where we have sand sediments and gravel sediments. And that's in all of the valleys that we have in California. This is a map of the groundwater basins in California, and I like to think of these groundwater basins as big giant bathtubs that are filled with dirt. These bathtubs are surrounded, or the bathtub walls are really the mountain ranges that we have. So for example, around the Central Valley, we would have the Sierra Nevada to the east, we would have the Coast Ranges on the west, and they continue under these valleys, and they hold the sediments that have deposited in these valleys over millions of years. So here's a cross-section through any one of these bathtubs, through any one of these groundwater basins. You can see here in gray we have the bathtub wall. These are the mountain ranges, fractured rock, fractured bedrock, and these basins are filled with sediments. This could be clay, silt, it could be sand, it could be gravel, and over time these sands and gravels, the pore spaces between them, has filled with groundwater. Groundwater is water that completely fills the pores in these sediments. The top of that zone that's completely filled with sediments is called the water table. And above that, we have the unsaturated zone, or the Vidau's zone. Rainfall and streams with water will recharge this groundwater, here shown as an unconfined aquifer, meaning that the water table is not restricted in how it moves up and down. So over time, these basins filled up with groundwater. And where this groundwater shows up eventually, when this bathtub, so to speak, gets to be full, is at the lowest part of these valleys. And that is usually where we have a stream. And that's where groundwater typically connects with our streams. Now, if I fill this up with more water from rainfall or from streams that come out of the mountains, and as they come out of the mountains and start flowing over these sediments, recharge this groundwater basin, I'm filling this up even more. And as a result, there's going to be discharge from groundwater into our streams. Groundwater flows from where we have high water table towards where we have low water table. It might not always move directly downhill. In some cases, it can well up because it's under the influence of the pressure from the high water table back here, and it will well up into the stream from below. So this is a natural way we have our system, groundwater being replenished from streams and rainfall that's not used by the plants that grow on the land surface, and then discharging into streams and also being used by plants that may be growing in these areas with very shallow water table. Now, the subsurface, of course, is a very complex sandbox or sediment box. It consists of many different kinds of materials, but if we divide the materials in sort of the coarser materials that we can actually use to pump groundwater and the finer materials that hold a lot of water but don't move it very much, these fine materials we refer to as aquitards. The coarse materials we refer to as aquifers. And on this image, I have showed the aquifers in blue, the aquitars in gray. And what typically happens is that our groundwater basins, the sediments in these bathtubs, are a complex sequence of fine material, aquitards, and coarser material, which are our aquifers. They're unconfined, closer to the mountains, and as we go to the center of the valley, we typically have these clay layers, aquitards, that then confine our aquifers. So just keep in mind that the subsurface is has a very complex pattern, and we can't pull groundwater out of every part of the subsurface, but there is a significant amount of groundwater. So we have the situation where we have recharge from rivers and rainfall and discharge into streams, and then in the 1930s, 1940s, we began to pump significant amounts of water from these groundwater basins in many areas in California. Here is a cartoon of what a well typically looks like. A well is essentially a borehole into the ground, and into that borehole, the well driller sets a well casing, which is slotted or screened in certain places, opposite of where we have these aquifers. And there's a so-called filter pack around this casing that makes sure that the fine materials that sit in the aquifer are not being transported into the screen and into the water that we pump out of this well. So this is how a well looks like in the underground. We have many of these wells, and they take water out, and as they take water out, they create what we call a cone of depression. So the water table around the wells is lowered, and it creates this cone of depression, which I indicate here. And the more we pump, the larger this cone of depression. Now, in the Central Valley, for example, this is from modeling efforts by the U.S. Geological Survey, we have many wells. We have literally hundreds of thousands of small domestic wells. We have many tens of thousands of agricultural irrigation wells. And then we have several thousand public water supply wells that pull groundwater out of the Central Valley aquifer system. These colors indicate how diverse the sediments are that these wells are penetrating. Only the red and yellow parts are really sandy and carry lots of water. The blue and purple parts are much, much tighter and don't carry as much water. So here you can see cones of depression, and you can imagine that as these cones of depressions increase and start to overlap, the groundwater table regionally will start to fall. Now typically we pump our groundwater in the summer when we use it for irrigation, and in urban areas also we really use much of our water in the summer, much of that for irrigation of lawns. Over the winter it rains, we pump less in urban areas, we don't pump at all in agricultural areas. We have more water in rivers that can recharge these groundwater basins near the mountains. We have rainfall, some of which might be recharging the groundwater, and the groundwater table will recover and go back to its original state. And this goes back and forth year after year. Now, one of the things that happens in California is, and we can see this year in 2014, we can have long periods of drought where we have much less water coming out of the mountains, much less recharge occurring, and where we do supply much of the water that we use for irrigation, both in urban areas and in agricultural areas, from groundwater. On this graph on the left side, you have the different water uses, including irrigated agriculture, here in this lighter green color. On the right side, this graph from the Department of Water Resources shows where all of this water that we're using is coming from. And this graph shows it for the years from 1998 to 2005. What I want you to focus on is this part, which is the groundwater, this purple part showing how much groundwater is being pumped to supply water on the left side. In a wet year like 1998, it might be as little as 12 million acre feet statewide. In a very dry year, where we rely predominantly on groundwater to supply water resources, surface water resources are much less, and we may be pumping as much as 20 million acre feet of water from our groundwater reservoirs. Now, one of the things that has happened in the last 10, 15 years is that we've had a lot of dry years, and as a result, looking forward from 2004 to 2010, we've had many years where we have used a large amount of groundwater, closer to the 20 million acre feet and not so much down to the 12 million acre feet. As a result, especially between 2007 and 2009, we have seen large amounts of groundwater levels declining. Now, most of that groundwater use, again here in purple, is in the Central Valley, the Sacramento Valley, more so in the San Joaquin Valley, and the largest amount is in the Tulare Lake Basin. There, water users on the top bar rely predominantly on groundwater. Also in some of the Central Coast basins, we have predominantly groundwater supplying the overall water supply used for irrigation and urban water. Now, there's some dynamics in this groundwater use, in this graph shown as dark blue. This graph shows both water use at the top, above zero, and then where water goes below this zero line. And you can think of this as a water budget for the root zone of our agricultural landscape. The graph shows an annual cycle going from October till September. And what you can see here is that there's a lot of water applied to our agricultural landscape in the summer between June and September, and much of that in a dry year is from groundwater, the darkest color. In a more wet year, much of the water that gets applied in the summer comes from surface water, the lighter blue colors and the medium blue colors, and less so from groundwater, which is this dark color. In wet years, we also have a significant amount of water that's precipitated onto this agricultural landscape and being recharged into groundwater. Much of that recharge happens in the spring and in the summer months, much more so in a wet year like 1998, and very little in a dry year like 1977. So as a result of agriculture and introducing agriculture into the Central Valley in the early 20th century, we have actually significant amounts of recharge, much more than under natural conditions, into groundwater aquifer. And this recharge out of these agricultural landscapes makes up a significant amount of the recharge into our groundwater basins. Some years it's more, some years it's less. And the further south we go, the more we vary how much groundwater we use. Again, the purple bar shows groundwater use. Some wet years, very little groundwater use. And in dry years, the groundwater use can double or triple or even quadruple. This is a groundwater basin in the southern part of the Central Valley. So we draw down these water tables. They may recover over the winter. They hopefully recover during a wetter period if we have multiple years of drought. But in some cases, we may be taking more water out of the groundwater basin than we're putting in, and in that case, water levels will decline permanently. Part of that consequence is that now we're losing the connection to streams, which ultimately, if they're not supplied by reservoirs, may actually then dry out, especially during the summer period. This is the situation that we refer to as overdraft, when the total amount of water going into groundwater is less than the amount of water that we're pumping out through our well network. Now, this is a graph showing the drought history over the 20th century, beginning in 1900 and going to 2010. And what I'm showing here specifically is the runoff of the Sacramento River and the San Joaquin River in the bottom graph. And what you can see is we have a sequence of wet periods in blue and green and dry periods in orange and brown. And in the last 15 years, we certainly had our good share of drier years, which has led to significant water level declines in many aquifers in California, but particularly in Central California, the Central Valley, and some of the coastal aquifers. This is showing you the total change in groundwater storage in the Central Valley between 2005 and 2010, which included the 3 drought years from 2007 to 2009. And you can see most of the impact is to the southern part of the Central Valley, the Tulare, what's called the Tulare Lake Basin, primarily on the east side of the Tulare Lake Basin, but also on the margins of the San Joaquin Valley and the margins of the Sacramento Valley. We have local areas where we have drawn down water storage in our groundwater basins significantly. In total, the Department of Water Resources estimates that drawdown to be on the order of 5 to 13 million acre feet between 2005 and 2010. As a result, the depth to groundwater is significantly deeper in 2010 than it was in the early 2000s. This is a map of the southern part of the Central Valley. You can see the area highlighted here from about Fresno to Bakersfield. In blue and green, you see areas where water table is between 0 and 100 feet below ground surface. In yellow, you see areas where the water table is between 100 and 150 feet below ground surface. And in red, you see areas that have a water table that's more than 200 feet below ground surface, and some areas more than 300 feet below ground surface. So this is one of the most extreme situations that we have here in the state. This is also from the Department of Water Resources, a compilation of the change in water level just over the last year between spring of 2012 and spring of 2013. And we'll probably see maps soon that show the same from spring 2013 to spring 2014. This particular map showing in yellow wells that have seen relatively little change, in brown showing wells that over that year have seen a change in water levels up to about 10 feet. And then you have many wells, especially down in the southern parts of California, but also in some of the northeastern parts of California, where we've seen significantly more than 10 feet of water level change between spring of 2012 and spring of 2013. Now, if I look a little bit closer and change the color scale on this, where now my yellow wells are those with drop in water levels from 0 to 25 feet, which is many of them. In orange, those that have a water level drop more than 25 feet, but less than 50 feet. And in red, you see wells that within that 1 year have actually changed by more than 50 feet. This gives you an idea of that water level drawdown during a drought period where there's no recovery of water levels in the winter, in the magnitude of how much water levels may change in this year if it turns out to be and continue to be a very dry year. So we're seeing water level changes that are typically on the order of 0 to 10 feet, maybe 20 feet further north. And down south, there are many areas that will see water level declines that are exceeding 40 feet. As a result of the long-term use of groundwater, we've actually created a significant amount of groundwater storage in the Central Valley. Again, this is from the California Water Plan draft for 2013, prepared by the Department of Water Resources. Much of that storage is in the San Joaquin Valley and in the Tulare Lake Basin along the east side. In total, the Department of Water Resources estimates that we have created storage space that we could fill up again since we started pumping that is on the order of 20 to 40 million acre feet, roughly the equivalent of the amount of surface water storage that we have available in the state. This storage we can use for conjunctive use of surface water and groundwater. We can hopefully use more of this space in the future to do groundwater banking during wet years and save water and store water for these longer term drought periods that we experience right now. But as a result of this long-term decline in groundwater levels in some of these areas, we have also seen subsidence, which is perhaps one of the most economically destructive impacts of this long-term decline in groundwater levels. Much of the subsidence has happened on the west side of the San Joaquin Valley and the Tulare Lake Basin in the Central Valley. Some of it has happened on the east side of the Central Valley down in the Tulare Lake Basin, with land surface levels declining by as much as 30 feet between the 1920s, 1930s when we first started pumping, and the 1970s when the State Water Project became available, and much of the water supply, especially on the west side of the Central Valley, southern Central Valley, switched to surface water supplies. But with surface water supplies tighter in the last 10 years, for a number of reasons, we have started to increase the amount of groundwater pumping. As a result, water levels continue to decline, and as you can see in this graph, the blue line showing the land surface elevation, that land surface elevation has also begun to subside again, very much in sync with the changes in water level elevations. And that could pose significant problems for infrastructure that we have in these regions, including the many canals that are all graded according to a certain slope. And there is damage that comes from these subsidence phenomena that needs to be addressed and would be very costly to repair. So let's talk very briefly about what do we do with the situation where we have groundwater levels dropping in some places. Sometimes they come up, sometimes they come down. There's a lot of uncertainty about how much water that actually reflects. Let me give you a little bit of background how, in principle, groundwater rights are organized in California. California has what's called the correlative rights doctrine. That means that landowners, which are not owners of the groundwater that is below them, but they do have what's called a usufructuary right. They have the right to use that groundwater. And the right to use that groundwater underlying a landowner's land is correlative to other land around the particular property. It's correlative to the properties of the aquifer and the amount of water that's available. It's a legal doctrine that was developed in the early 20th century and that governs the overall way we share groundwater within a groundwater basin among many users. We have a constitutional mandate to use all water for beneficial use. You cannot use water just to waste it. We have many special districts that manage water, that are used for many different purposes. We have water districts, we have irrigation districts, we have water conservation districts, and many others. Counties have, under their police power, the right to control groundwater exports out of county. In Southern California, many basins have experienced overdraft back already in the early part of the 20th century, in the middle part of the 20th century, and as a result of that overdraft have either been forced to or have agreed on doing what is called basin adjudication. In the case of basin adjudication, experts look at how much recharge there is into a groundwater basin, and the stakeholders agree on or are somehow dividing up that amount of replenishable water that is going into their groundwater, and they divide it up, and everybody essentially gets a given right, a numerical right to how much groundwater they can extract, very much like we do distribute surface water rights, which are quantitative rights to specific amounts of water. These basin adjudications cover most of Southern California, but there's only one that is in Northern California. The State Water Resources Control Board is the agency that's overseeing groundwater management in the state of California. And it's the courts that ultimately decide, if there's multiple parties that cannot agree, on who gets how much water. But we also have groundwater management plans, which came about in the early 1990s and which we have improved on in terms of how we manage groundwater plants. About 42% of groundwater basins in California have some form of a groundwater management plan. In lighter green colors, you see groundwater management plans that have been prepared under the particular structures of what's called Senate Bill 1938, which cover about 32% of all groundwater basins. Those adhere to significantly tighter management practices and assessments than some of the older groundwater management plans that have been done in the 1990s. Groundwater management plans include many different pieces. For one, there is a planning process. They define governance structures. They define agreements on goals, reporting, and enforcement, at least ideally. There's cooperation among stakeholders. In preparing for a groundwater management plan, organizations identify and engage participants and stakeholders. They develop structures to involve stakeholders. And they try to facilitate disputes, trying to resolve disputes prior to going or avoiding to go to court. A big part of a groundwater management plan is to collect information about groundwater, to find out what is there, to collect data, to make those data available to do the analysis, and have a portfolio of management practices that can improve on groundwater conditions in a particular basin. So California has a sort of a minimum list of elements that go into a groundwater management plan, which includes a basin description, it includes a description of the governance, it includes the specification of specific management objectives for a groundwater basin, it includes the monitoring, that is the collection of data, and some form of accountability and review built into this groundwater management process. Where we currently have challenges is with enforcement mandates. Who actually tells a groundwater pumper that he or she needs to stop groundwater pumping if there is overdraft? Who makes the decision that there is overdraft? Under what conditions do we stop groundwater pumping, and who makes those decisions? So there's a number of challenges that we have also with respect of integrating groundwater management with surface water management, which now happens under so-called integrated regional water management plans, which also have governance structure. So many groundwater management plans are now part of integrated regional water management plans. Also integrating water quality and water quantity is something that we will see more and more and as we move forward managing our water resources. And one of the biggest political questions is what is the role of the state and what is the role of local and regional agencies? The State Water Resources Control Board recently emphasized that it is pursuing and is interested in pursuing a primarily local regional management approach to groundwater management, but still it has an oversight role, and defining that oversight role will be something that we'll be looking at in the next few months and couple of years. Here is finally a short list of some of the resources that I have used for this presentation. I want to thank especially the Department of Water Resources for the resources they have provided. Thank you very much.